Hello everyone, thank you for viewing my presentation evaluating the security of a prototype for an airport CT baggage screening system. This presentation evaluates the security of a Heathrow Terminal 2 CT baggage screening prototype. It's a simplified design, not for full functionality, but demonstrates a secure by design approach across requirements, design, implementation and deployment. I'll show how sensitive data such as scan events and threat imagery are protected, how risks were identified using a stride threat model, and how those risks were reduced using controls aligned to the OWASP top 10. I'll then assess the remaining gaps in control coverage using an ISO 27001 aligned approach. This will include a risk register and treatment strategies, and will identify any gaps in control coverage, finally concluding with what would be required to move towards a production-ready system. The prototype's got some key limitations. It's not connected to a live CT scanner, and it does not include any AI-based threat detection. Instead, we'll use publicly available X-ray imagery, primarily due to the sensitivity of such real data. I'll now demonstrate the prototype and show how the security controls behave in practice. Notice that the application is served over HTTPS. So firstly, I'll log in as a lane operator. The authentication uses hashed passwords with session hardening, including secure cookies and session regeneration. Once authenticated, I'm presented with a scan event dashboard. As a lane operator, I can only view events for my assigned security lane. This restriction is enforced server-side using role-based access control. Now, if I open a threat image, you can see it's not exposed as a public file. Instead, it's served as an authenticated endpoint which checks authorization before returning the image. I'll now log out and will sign in as an administrator. Administrative functions are restricted to privileged users. So here I will be able to modify the operator permissions. I'll update the operator to allow access to an additional lane. So there we go, give him lane 2. And this action is recorded in the audit log, includes the actor, action, target and timestamp. That ensures accountability for privileged changes. I'll now log out and sign back in as the lane operator. Now, after the role change, you can see you can now view events across both assigned lanes. So this demonstrates the role-based access control is enforced dynamically based on server-side permissions. Now, overall, the demo shows how authentication, RBAC, protected media handling and audit logging all work together to reduce risks such as unauthorized access and privilege misuse. Before we look at any controls, I wanted to state the basic requirements that shape the prototype. Functionally, the application needs to provide operator login, store scan event data persistently, display those records through a dashboard, and support administrative account management. From a security perspective, it needs to restrict access by role and lane, protect threat imagery from direct public exposure, and preserve accountability for privileged changes. If we build security from the onset into the requirements, it matters because it shows a fundamental tenet of secure software design principles, and that security was part of the original system thinking rather than being added as an afterthought. We can therefore be more confident that risks were considered and mitigated in an appropriate manner. An application designed in this way would be easier to treat and less expensive to patch and maintain should future vulnerabilities be detected. I also want to make the secure by design approach explicit. In this project, security was considered at all stages of development. The three core objectives we need to consider are confidentiality, integrity, and availability. Confidentiality matters here because scan events, operator accounts, and threat imagery should only be visible to authorized users. Integrity matters because roles, session state, and stored records must not be altered improperly. And finally, availability matters because the dashboard should remain usable for, in this case, demonstration. However, this prototype does not yet include full production resilience. Stride and CIA are complementary together here. CIA defines effectively what I'm trying to protect, and Stride helps structure how those assets might be attacked or undermined. Moving on to what this assessment covers. So we start finding the scope of the assessment. In scope are the web application, operator accounts, scan records, threat images, and the supporting LAMP infrastructure, including Apache, MySQL, and PHP. We have additional Docker and Nginx components in scope. The user roles in scope are the lane operators, managers that we haven't looked at, and administrators. The permissions assigned to each role have direct security implications. Out of scope are the physical CT scanner hardware, the wider airport systems, central identity services, and the AI computer vision pipeline that would be needed for automated threat classification. I'll treat the scanner to application API integration as also out of scope for this prototype. Here we've used seeded events rather than a real-time feed from CT equipment. Likewise, 3D CT imagery and annotated bounding box datasets are also out of scope. That links back to the AI. At the same time, a real airport deployment would sit inside a wider operational environment. You would have things such as physical access control, staff processes and procedures, network controls, and security response. So we'll keep the assessment focused primarily on the prototype, whilst we still want to acknowledge that we live in a wider live lane airport, and therefore when we do build such secure systems, not all controls should be considered technical controls. Because this is also a development exercise, I added a simple project plan to show how the system was built. So I defined the requirements, scope, assets, and any security objectives. Then designed the main modules, authentication, session handling, the dashboard, image handling, operator management, and deployment. Then went on to implement each module with security controls rather than attempting to bake them in later. At each stage, I tested the main functionality and any security behaviours such as RBAC, session handling, validation, and so on. And finally, I reviewed the completed prototype through a gap analysis, risk scoring, and additional threat modelling. A fuller module by module version of this plan is in the appendix. No good software project would be complete without an architecture diagram, and here it's quite useful to show the architecture and any trust boundaries. We've got some key boundaries here between the user browser, the client, and Nginx over HTTPS. We've also got a boundary between Nginx and the PHP application inside Docker. There's an additional boundary between PHP and MySQL, although it's not shown on the diagram. And also we have an external boundary layer between the system and the external airport infrastructure. These boundaries are quite useful because it helps Stride become much more concrete, and we can tie it to real data flows rather than fairly abstract categories. Before looking at those controls themselves, it's useful to state the most credible attack paths. The main ones in this prototype are credential abuse, unauthorized access to imagery and scan data, and misuse of privileged administrative functions. Controls in the next slides were selected to reduce realistic attack paths in the architecture rather than being selected in a haphazard manner. You could argue that certain security controls should be in place by default, regardless whether an attack path has actually been identified. So a simple attack scenario. Imagine an attacker targeting the login page. They could be using reused, guessed, or otherwise obtained credentials, such as by a phishing attack. If that succeeds, the attacker could gain access to scan events, threat imagery, and perform functions that they weren't permitted to do. This is where the controls matter. We could implement password verification, throttling, secure session handling, and role-based restrictions, all to reduce that attack path. We do have some residual risk here because multi-factor authentication is not implemented, and we also use seeded credentials at deployment time, so there is the slight chance of some credential leakage. The prototype was developed containing a number of security controls and best practices, creating a baseline. Authentication is protected by hashed passwords, login throttling, and session handling. Authorization is role-based, and lane operators are restricted to their assigned lanes only. At the coding level, we use prepared SQL to reduce SQL injection attacks, CSRF protection, server-side validation, and output encoding. The threat imagery is controlled by a protected media endpoint outside the web root, so these files aren't just exposed as static assets, and you must be authorized to access them. At the edge, HTTPS and security headers are enabled. I also implemented administrative audit logging, and in the demo you saw that as I authenticated as a lane security officer with access to view only the security events for that assigned lane. This shows the RBAC controls. Here we can see the login flow using PHP's password verification functions rather than plain text or reversible passwords. Repeated failed sign-ins are tracked and locked out after 5 failures. Also on successful login, the session ID is regenerated to help prevent against session fixation attacks. Secure session cookies. Application expires sessions after 10 minutes of inactivity. So in Stride terms, these will reduce the risk of spoofing and also reduce some level of elevation of privilege risk. Should be clear that the access control here is quite simple. Authentication is handled inside the prototype. In a real deployment, I'd expect this to be federated with the airport's own identity access management system rather than standalone local accounts in the application. Next major control area is authorization. The application requires authentication before users can access the dashboard or the JSON data endpoint. Administrative functions are protected separately, so only admins can manage operator accounts. Threat images are also protected quite carefully. They're not public static files and are authenticated through a PHP endpoint. So in Stride terms, that addresses the issues regarding information disclosure and elevation of privilege. Also includes some defensive measures against fairly common web threats. Database access using prepared statements throughout, reducing SQL injection. Requests are also protected with CSRF tokens. Validating the input server side, that includes roles, lane numbers, filters, and any access to external media. This mainly reduces the risk of tampering and information disclosure if we map it to Stride. Also align with the best practices highlighted in the OWASP Top 10 with respect to injection, cross-site scripting and access control issues. Also included are transport and browser hardening. We've got HTTPS in place and only the TLS 1.2 and 1.3 algorithms. Various HTTP headers are set, HSTS is set. This is where the value of Nginx becomes clearer. Because it sits in front of the application, it provides a fairly straightforward place to terminate TLS and apply browser-facing security controls at the edge. It's frankly easier to implement in Nginx than it is in Apache or PHP. Also, I've made sure that the MySQL port is not exposed directly to the host, so it's only accessible via Docker services. So in terms of Stride, this would help reduce information disclosure and tampering risks. To a certain extent, it will also resist spoofing. There are limitations. The certificate in this case is self-signed. In production, obviously, you would need to produce a full valid certificate. This is fine for a demo. For accountability, I added an admin audit logging, so who did what, when and where from. This mitigates the repudiation risk in terms of Stride. Without it, the admin could plausibly deny having created or changed an account. Here we look again at our mapping between our controls and Stride. I will have attached the presentation to the video, so you can look at these in a little bit more depth at your leisure. The next question is what has not been implemented or what remains incomplete. Firstly, there's no MFA, multi-factor authentication. We've also used demo accounts and seeded credentials when initializing the database. You'll find those credentials are also present in the Docker Compose file. Managers have got a fairly broad visibility across the environment rather than a least privileged view. Authentication and access management are also local to the prototype rather than being federated externally. Threat images, whilst they're access controlled, they're not encrypted at rest. So things like encrypted drives would be used there. Logging is only limited to admin changes. So there's no sign-in logging, failed logging, so on and so forth. Finally, there's no documented backup, restore, monitoring or recovery processes. So these gaps are quite important because they show that the main residual risks are present. However, they're primarily limited to sort of operational and architectural rather than coding failures or omissions. I condensed the gap analysis that we can find in the appendix into our highest value areas. Strongest parts of the prototype are the application layer controls themselves, such as authentication, RBAC, secure coding principles, reducing the exposure of the database by being an internal only service. The weaker parts are mainly the operational controls and also things like secrets handling, limited logging, and fairly weak resilience. I've framed all those gap areas using an ISO 27001 approach, using relevant Annex A control themes. Now, in a real airport environment, we could reduce some of this residual risk with non-technical controls, such as secure rooms and cabinets, restricted physical access, CCTV, training, security response, and so on. Looking at the risk scoring method, simple scale 1 to 5 using our impact times likelihood approach, calculated the score by multiplying them. So in this model, any score above 10 or more requires some explicit controls and treatment. I performed the assessment twice, first with no controls in place, meaning the application without the relevant safeguards, and then again in a controlled state with the implemented controls. This gives us a clear before and after picture and shows how much risk reduction the safeguards can actually achieve. So just showing some examples there of, let's say, for example, unauthorized media access with no controls, but as soon as you put the authorized endpoint in place, it drops down from a 20 scoring down to a 10. So overall, in terms of an application, my judgment is a fairly credible prototype, suitable for an MSc summative. However, as it demonstrates some real controls rather than just a checklist. We've got authentication, authorization, secure coding, media handling, TLS endpoints, audit logging, all implemented. So in terms of CIA, I can say that we addressed confidentiality most strongly, integrity fairly well. However, availability is supported at just the basic prototype level and is nowhere near an operational standard. Any remaining outstanding issues are not trivial to implement. Things like MFA is a non-trivial task to implement. However, we've also operational and deployment gaps that will take it from a proof of concept to a full production deployment. So ultimately, the prototype isn't insecure, and it's reasonably secure for a controlled demo, but we will require further hardening before it moves anywhere near production. So some recommended actions, so some quick wins really. Remove the seeded demo credentials and require unique passwords. Move the database and application secrets out of the configuration and Docker Compose. Extend our audit logging. Improve the role in terms of principle of least privilege for the manager. Add backup, restore, monitoring and incident response processes, and replace that self-signed certificate so that it is no longer just suitable for a lab. However, that required me paying for one, which I wasn't going to do. So here's some references here in Harvard style. They're there in the presentation slides for you to take a quick look. Main frameworks used were the ISO 27001, Stride for threat modeling, and the OWASP top 10. I kept the main presentation focused on the highest value risks and controls. However, the full risk register, gap analysis and project plan are included in these appendices for completeness. Once again, thank you for viewing my presentation today.